this is the spectrum of hydrogen. Notice there's 3 distinct emission lines. Likewise, if argon is put in a tube and subjected to voltage, argon gives off these very characteristic lines. Sodium, like from a star or from a furnace, or perhaps in an acetylene flame, will give off these emission lines. I particularly like this graphic. This is sodium from the Earth. This is sodium from a nearby galaxy. Notice it's the same, but it's moved over a little bit. This is sodium from a faraway galaxy. Notice that it's moved over even farther. Sodium gives off a characteristic emission spectrum, and that's the way it is. If the spectrum has been moved, it tells us that the object that emitted the sodium light is moving away from us, and furthermore, the more it's shifted, the faster it's moving away from us. This, of course, all relates to the expansion of the universe. The boundaries of Solvinsky's box are very much not clear, but I would say that the electromagnetic spectrum probably does not go into Solvinsky's box. This is due to engineering marvels of our age and generations of scientists, but I think that you can run light through rainbows and diffraction gratings, and I think the electromagnetic spectrum is pretty much falls into our understanding. There are some very strange things that go on in Solvinsky's box. We need an example. I want to use bullets, and we need a set of calibrated targets. Let's use vases. There's 1,000 vases. Vase number 1,000 is so hard that it's hard to find a bullet that will break it. And vase number 1, any bullet will break vase number 1, and they're calibrated. So 1 through 1,000, getting harder and harder. The vase either breaks or it doesn't. It's a pass-fail test. We have a bullet. The bullet will break vase number 495. It will break vase number 495, but it won't break vase 496. So obviously, if it will break 495, it will also break 494 and 493, etc., etc. So the bullet will break every vase up to 495, but it won't break vase 496. There's an energy associated with a bullet which is related to its weight and its velocity. Okay, let's move to a photon. We have a photon, and the photon will interact with a certain energy transition. It's the energy that matches that transition. So one would say that, well, if it will interact with this energy transition, it should interact with those requiring less energy. But that's not the case. The energy of the photon has to match the energy transition, and if it doesn't match, it doesn't matter anymore. It would be like the bullet that we're using will break vase number 495, but it won't break 494, and it won't break 496. So the energy from the electromagnetic radiation has to match, and if it doesn't match, it doesn't do anything. This is not a particularly difficult concept. This is Solvinsky's box, and it's not a particularly difficult concept, but it's very important to understand that the energy from the electromagnetic radiation has to match the transition, or it doesn't do anything. Okay, let's look at the electromagnetic spectrum in a little bit more detail. X-rays are kind of the big bad guys of the electromagnetic spectrum. X-rays they're really too energetic even for most molecular structures whatsoever. X-rays go through pretty much, well, they go through covalent bonds, that's for sure. Like things like tissue, water, organic materials, if they have a lot of water in them. They don't go through bones. They don't really go through wood very well. things that are very dense with ionic bonds are absorbed by X-rays, but X-rays are very, very powerful. They're not generated in nature. The sun doesn't really produce them. They're not generated here on Earth except for by instruments. And of course, they're used in the medical community to image things that we can't see otherwise, i.e. bones inside of the human body and other things. Ultraviolet radiation is at a frequency where it impacts on covalent bonds, so that like pi bonds and sigma bonds are impacted by ultraviolet radiation. So sigma bonds can get activated, can go into a higher level. Pi bonds can go into a higher level. Ultraviolet radiation is destructive in that it breaks down organic materials. The sun produces tons and tons of ultraviolet radiation, but fortunately for us, the great majority of it is captured in the stratosphere in the form of ozone. Apparently, ultraviolet radiation striking oxygen forms ozone, and then the ultraviolet radiation from the sun is also absorbed by the atmosphere, so that by the time the UV radiation reaches the Earth, there's not very much left, and what little there is right outside of the violet range, and it's useful for things for living organisms. Like some insects can use it to see. It's not particularly penetrating, but a little bit. Human beings use it to produce vitamin D. So as we go down the electromagnetic spectrum, we get to visible light. Visible light is like it's like the Goldilocks zone of the electromagnetic spectrum. Visible light impacts upon the valence electrons and has the potential to do chemical reactions. The overwhelming example of this is that the blue and violet, what we see as blue and violet, are used by plants to capture energy. They take the energy from the blue and the violet, along with carbon dioxide and water, and make it into glucose. Visible light comes from the sun in absolutely enormous amounts, and it's not particularly absorbed by anything coming down through the atmosphere. It's just absorbed and dispersed by water a little bit, but it goes through water for the most part. Enormous amounts of regular light reach the surface of the planet, and they bounces around, and there's light absolutely everywhere, especially during the day. Our eyes are designed to capture these random photons, and there are chemicals in our eyes that make conformational changes and produce neural impulses and allows us to see. It's not too hard to imagine that these molecules have the potential of absorbing different frequencies differently, and then our brain is able to see colors. Let's turn our attention to this model. This is propane, rather common. It's a gas. Of course, it's flammable and used in barbecues. A propane molecule kind of has a life of its own. It like wiggles and jiggles, and the bonds stretch and bend. Textbooks describe these as being on springs and following harmonic motion. And then the springs have different sizes, both for their length and for their stretchiness. And the harmonic motions of the stretches correspond to the frequencies, which are in the IR range. And that's fine, but I think we have to remember that the changes in the conformation have to do with changes in the electron structures. These are quantum changes. Electrons disappear on one level and appear on another level, and a quanta of energy is either absorbed or released. So as the molecule is wiggling and changing, electrons are going from state A to state B, releasing and absorbing a quanta of energy in the infrared region. Let's move to this guy. This is a block of wood, similar to the propane. It has molecules in it that are moving and jostling. The great majority of the electromagnetic radiation is radiated and absorbed within the block, But right along the surface, there will be infrared radiation which is radiated out. My studio is surrounded by things like this, and it will also be giving off infrared radiation so that the block is in equilibrium with itself, and then the block is in equilibrium with the room for this radiation. This, of course, very much relates to heat and temperature. If this block is put in a situation that's perfectly thermally insulated, like in a vacuum, it will come into equilibrium for the temperature with the surrounding because of this radiation. I never really understood that until I made this video.